Meine Damen und Herren, willkommen, bienvenue, welcome. I would like to welcome you all to the final day of content. And of course, as I have been saying before, there is no new content. We're simply applying what we've been doing. It's the same one equation. Change in energy is total work not accounted for. But we're going to apply it and we're going to hopefully compactify and make some sense of it. That's the goal anyway. Then next week, Monday, we're reviewing in a bit of a blur. We're reviewing kinematics and dynamics. And then Wednesday, we'll do rotation and energy again, and then it's final season. So I have a scenario to do today. We're going to go back to elevator land. Oh God, she says, oh God, indeed. Yes, it is the God of physics. Now, so you can pray to go up and not down. I'm stretching it too far. What else? What else? There is a procedural announcement. Let me remind again the people who are wise enough to be here and or online and paying attention. There will be a homework 12 posted. It will have a note in it not to submit it. I am warning you now. Again, do not submit homework 12 unless you wish to lose points. I put together the thing of I gave an extension for 11, but I've got a lot of people not paying any attention to directions. So there is a homework 12 that is extremely more optional than anything you've ever taken before, which is to say, if it's got bold letters on the front that says do not submit, and you will lose points. And I am telling you twice in lecture, both on Monday and Wednesday, do not submit homework 12. Then anybody who is really not paying any attention whatsoever deserves what comes to them. For what it's worth, they're going to be valid, worthwhile exercises that will stretch you. They will be challenge exercises on these topics. It's not about botany or whatever. But do not turn it in. You have been warned. It is your choice whether to warn your classmates who do not read instructions, do not watch the YouTube video, do not read the instructions that are printed on the top of the form. Oh, by the way, this is not a mastering. You will see no 12 on mastering. This is on, this will be a PDF with the instructions written on the front of it as well. Okay. Yeah, you see? Makes sense? Homework 11, the homework that was theoretically due last Sunday, I didn't put a placeholder in Canvas, so I gave an extension. You've got until tonight to finish it off. 15 problems. Okay, incidentally, we have a very special visiting guest here today who may walk around and assist with the mathematical side of things, Dr. Cerny Joshua, and also future Dr. Nalo Tucker, who is currently at who has to running around. Dr. Joshua, as I think I bragged on the very first day of class, is quite literally an expert in mathematics education. So she did her PhD on. She's also got a degree in physics, a bachelor's, not a PhD in physics, but she does actually know what she's talking about. And if she comes over and looks over your shoulder and gives you a pointer on the mathy side of things, I encourage you, listen to what she says, because she is a far better math teacher than I am. I have learned to teach math by necessity. She has studied how to teach math for years of her life, focusing on that with actual world experts. Okay, so Dr. Joshua, would you like to say a word or two? Oh, and I forgot the people online are keyed to, no, it's not this microphone. They should be able to hear you as long as this is turned.
Have they heard everything you said just now?
Yes, yes.
Okay.
It's not keyed to the mic.
Okay. Hi, everybody. Ross asked me to come because, like many teachers, he goes home and worries, oh my gosh, what can I do to help the kids, the students, sorry, I'm used to K-12, that aren't learning very much. Last period was very silent. Is that typical?
Yes.
Okay. So I'm telling you that the best way to learn, even if you're stuck, is to just talk about it. I'm going to ask you to do something brave. If you are not sitting next to someone, can you get up and move a couple of seats over? Not going to make you, but let's see who can be brave enough There's only a few more classes. Stand up and just walk over to someone so that there's one more seat. See, she did it. She's brave. Come on. People in the back, can you guys move together? You guys right here, move together. Just have one person to talk to. They're together. Are you brave enough to move? Oh, look at he's doing it. What about you guys? You don't have to move seats, just kind of scooch towards each other. I got someone over there all by themselves. You brave enough? Brave enough to move? Can you talk to the person in front of you? Oh, look at that. Thank you. Okay, when he asks you to talk, even if you don't know what to do, talk about how you don't know what to do. Do you know what I'm saying? Especially, yeah, you need to talk more if you don't know. And just by talking about it, then it might trigger something because putting things in words clarifies our mind. Does that make sense? Also, if you're talking, he can walk around and hear your question and be like, oh, here's a little hint to get you unstuck. Sound good? All right, your goal is to be much louder than last hour. Last hour, sorry, I'm again. Thank you. I'll walk around and help too, but
I'm mic'd. This
do I
is
just ignore?
stuck somewhere in the Google form, thou shalt ask a question. If you precisely describe where you're confused, could you say that again? I don't understand how to apply X. If you tell me what you are struggling with, I will address that. I will address that for everybody who is also probably struggling with the same darn thing. It's not just you struggling with any given topic. Okay, so also that applies for the people online asking a question in the chat or pointing out that I didn't turn my mic back on. Very helpful. I don't think there are any other administrative details. Let's dive into some physics. Oh dear. Okay, so Dr. Joshua did a much more artistic, nicerly sketch of the scenario that we've got going on here. Let me copy this into our thing. Yes, I appreciate you so much, Squirrel. I mean, Dr. Joshua. Copy. So our scenario is as follows. We are in an elevator, an elephant vader. And we are going to start 4 meters up. We are in the process of moving up. We're going to be having an initial velocity. We are going up. We go past the 3rd floor, past the 4th floor. And just as we're passing the 4th floor, some diabolical 9-year-old snips the elevator cable and we plunge to our doom because he also sabotaged the brakes, which are actually supposedly really fail-safe in that. And then we smack into a spring at the bottom, which of course saves our lives because I think the values I've chosen might possibly accelerate, slow you down at a reasonable rate. Well, let's find out. We can do that at the end if there's time. Okay, so we're going to break this into 2 parts. I want you to analyze what is going on while the cable is moving us up steadily and stably, passing the 2nd floor, about to hit the 4th floor. And then we're going to analyze the process of the cable gets cut and there are no brakes. We fall to our, hopefully not doom, compressing the spring. Focus on the first part now. We started at a height of 4 meters above ground. Our initial position is 4 meters. Oh, well, here's a very good question here. I want to ask you this because, as I've said 4 times, your 0 point, your reference point, your where y equals 0 is, does not actually matter in the problem as long as you're internally consistent. You are free to pick this as 0, this as 0, this as height y equals 0. Any point can be y equals 0 if you so choose it. As long as you then remember that's where y equals 0 for potential energy calculations. Yeah? Let's have a show of hands. Who wants y equals 0 to be here? Oh, wow. Okay, great. There we go. The vote is quite easy here. Oh, well, that's erasing the K. I'm going to define y equals 0 meters to be there. And again, what does that say? What does that tell us? Why is y important? Exactly. MGY is 0 if you're at y equals 0. We're going to have an MGY at least the first 2 phases of motion. Capiche? Yeah? Make you sensey? Great. So I'm going to give you the mass of the elevator is too small to be seen here. Mass of the elevator, let me be also precise. The mass of the elevator and the stuff inside it. The mass of the system is 2,000 kilograms. You are also free to define the system as you choose. We could talk about the passenger as a separate object from the system. Then there would be more forces, more works, more energies to consider. Let's keep it straighter forward and say that everything inside this red dotted line is the system, and we're not going to consider internal forces. Okay. So mass of what is inside that dotted line, mass of the object under study is 2,000 kilograms. I'm going to say that your initial velocity is 1.5 meters per second, and your acceleration, at least at the beginning, is 0 meters per second squared. Yes, round G. Okay. Each floor is 4 meters. That's why it says 4 meters here. And I'm going to say, as you go from the second floor, as you are starting moving past the second floor, and then you hit past the 4th floor. Are we stopping? No, no, we started in motion, we're continuing in motion, but I want you to analyze from the 2nd floor and as you pass the 4th floor. Here's what I want you to analyze. Here are questions that you should be able to answer. Question A is we're simply going to identify the force or forces acting on the elevator, on the system. Part B, identify energies. Energy or energies. Let me put this as a separate thing. Identify energy or energies. Is there external work? Which I think I've been writing as W external. That's the question. To describe this, unless you have a question or whatever, I would like you to identify forces just by the single letter abbreviation. To identify the energies, K, UG, UE, and is there external work? I'd say that's a yes or no question. We'll talk about if there is one, and what form or forms, what force or forces are causing it. Okay, that fair? Question. Yes or no? Is there external work? Yes. Is there external work? No. Y or N? Yes or no? Yeah. Nah, it doesn't need to be triplet notation. We'll practice that on Monday. But for A, just the single letter that identifies the kind. What force or forces, energy or energies, work will you consider when we're talking about motion from the second floor or passing the second floor through passing the fourth floor? Any other clarifying questions about what the system is, the scenario is? Okay, get a start, and please, as Dr. Joshua suggested, please talk to each other. It helps. Give it a shot.
Is outside of the red box, and that's what we call the system. Would that mean there's external work?
Very good. Very good. Well, I mean, the Earth is outside the red box. The Earth exerts a force. Would you consider that an external work? What do you think?
Gravity's always there, and I feel like sometimes we just don't consider it because we know
True.
it's there. So,
Sometimes we don't.
so I don't know if in this case we would consider it because the tension of the cable's pulling it up, but the gravity's working against it. So would it also be considered an external force then?
The correct answer is actually either way you said can
Oh.
be considered correct. You have a choice. You just can't take both choices.
So you either
You could call it a work. You could call it work, or you could call it potential energy. Since we are going up and down, you can't ignore it completely. It has to be either work or potential energy. If you consider it as properly, if you consider it as external force, there is a weight force acting, we would talk about it as a work. Or we could say, I am moving up, I am storing the ability to move downwards, storing the ability to fall, to speed up as I go down. That internal energy, that would be considered as a potential energy.
think it. For A, to identify force, so kind of like normal force, but
Good, good. I mean, I shouldn't say, yeah, no, I can say yes. That is correct. Yeah. Is there a force that is acting on the system that is not inside the system, like, the person on the elevator, that work cancels? We're considering the stuff inside the system as part of one object. So don't talk about the work of normal force on the foot. And also force that we have not accounted for in other ways. If you're compressing a spring, don't talk about the work of the spring if you're also talking about its spring energy, if it's spring potential energy. We're talking about work done by gravity. Don't also talk about gravitational potential energy. You can't double count. So actually,
Sorry,
wait,
potential weight force. And then for the
correct. That is unambiguously correct.
settings kinetic and gravitational stuff. If we could clarify that.
That's correct, but then that changes your answer for what forms of work are there?
So see,
Is there any force acting that's not already included?
I was listening about this.
Sorry, please.
So basically, like, for your C, we can't say that it's weight force, because we can't,
Yeah, we already said that in the
Yeah.
beginning.
It's not weight work.
So anything else that we haven't considered?
Correct. Is there anything else that you're not already counting as gravitational potential?
Oh, I see what you mean, but this time we're not considering the person inside, right?
Well, that's an internal, yeah, never considered.
We need an example of what.
Well, look at the force list. Tension. Tension does work, unambiguously. There is no potential energy of tension.
Oh,
that makes sense.
That's why I had you do part A.
how's it
Makes
think?
sense.
Good. Good, 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 and good questions. Okay, 30 seconds.
For notation for lift, didn't want to have two E's in there.
Yes, but I was just saying use a single letter for the kind. I don't need to do the triplet. But sure, no, it's fine. You're right, you're right. Also, I realized, haven't I been talking about the spring forces Fs? And also the static friction forces Fs? I'm such a big silly since we weren't doing them in the same module. I didn't even notice that a symbol collision was happening. We're going to change the name of spring force to just capital S. Do that later, yeah. All righty, let's bring it together. Forced off, let's identify the forces. Forced off, we'll identify the forces. When is there normal force? When there are two solid surfaces touching. Well, I see a solid surface touching. Is that a tension? No, for God's sake. I meant to say normal, and I said the word that came out of my mouth was tension. There is a tension when there is a rope, string, cable, or chain. Is there a cable? So should you include tension? Yes. Now the question I meant to ask, when do you find normal force? Two solid objects touching each other, exactly. Is there a solid object pressing against this elevator? No. Well, there's a kid inside the elevator, but that's part of the system. Good. You have the choice of whether to consider it internal, external, part of the system or not. We have chosen to get it considered internal, so it's not an external force. We won't do an external work by that normal force. Okay, so, normal, no. What about friction? Why no friction? Huh. Well, I'd say there's nothing going against it, keeping it from moving up. The side rails are usually pretty darn smooth by design. I would also say, because you don't have any information that indicates there is friction, and we always make the simplest set of assumptions, right? I didn't indicate anything about rails that have a mu constant. And if I don't mention it, there's a big hint if I'm not including that information. Now, we could, if we make reasonable time, we could include that in part C, talk about the work done by friction, but not in this part. Is there a spring in the problem? Well, I see one down here. Is there a spring force acting in this part of the problem? No. There might be a spring on the diagram, but if the spring is not touching the elevator as it rises, it is not exerting a spring force. Again, if he no touchy, no acty. Weight is the only long-range force. Springs do not push on you if you are not in contact. In the second phase of the problem, we're going to talk about the elevator slowing down as it spring decelerates it, right? Then there will be a spring force. All right. So the correct answer for A was tension and weight. B, identify the energies. I gave a big hint earlier. Well, someone, I forget who, someone gave a hint earlier. Excuse me. If we define this as height 0, y equals 0, then mgy is not 0 up here. Gravitational potential happens here. Gravitational potential happens anytime you're not at wherever you have defined y equals 0. We are not at y equals 0. We are going up. At the end of the problem, we're going to be on the first floor in contact with the spring. I'm going to call that close enough to 0 to be at the reference point. Okay, so the spring is not actually a point. Ignore that. So for part B, we are absolutely going to have potential energy, both at the gravitational potential energy at the beginning, gravitational potential energy at the end. Spring potential energy? No way, Jose. I'm not touching the spring. The spring is not compressed. The spring is not extended. There is no energy stored in the spring just sitting there. Kinetic energy, are we in motion? Bazinga! At the beginning, at the end, absolutely. External work, is there any force external to the system that we are not accounting for in the form of gravitational potential energy? Is there any force acting on this? Look at your list from part A, any force acting on it that we're not accounting for as a potential? Yes, tension. If we wish to analyze this in energy perspective, there will be an external work done, just the work of tension. We are listing separate things in part A and in part B. In part A, I ask you to identify the forces. In part B, I ask you to identify the forms of energy, but tension is not an energy. Tension delivers energy by doing work. So did we already account for it? We're not writing our equations yet. We're simply saying, do we have this, that, or the other form of energy? Tension is something that does an external work. Tension is an external thing that does work that we will have to account for. Work isn't an energy, though, any more than a paycheck is a bank account. Paychecks change your bank account. Paychecks and bank accounts are measured in the same thing. It makes sense to add paychecks to bank accounts to get total worth, but I distinguish between former forms of energy and is there force delivering, causing there to be a change in energy? See the distinction? Please.
If I'm understanding the question right.
Please.
So by W external, we mean that on the system, there is a force and the displacement. So it's like Fs cos theta. So since the tension is in one direction and the displacement is in the same direction, there will be some work.
There will always be an external work if there is a force that has not been accounted for, like weight. That force might deliver positive or negative work, or if it's at right angle zero work. But anytime there is an external force that is not already counted for in the form of gravity or springs, then there will be, you could talk about the work done by it.
So I'm getting it right.
It doesn't matter that they're both up. Them both being up means the work is positive instead of negative or zero. You can always calculate the work by every force acting on the object.
But like still, the directions are at 90 degrees.
Then the value of the work is zero. Zero is a valid value to have.
So that will be counted in the work.
I suggest you always consider every force acting on an object. If it's already accounted for in the form of a potential energy, cut that out. Ignore spring energy. Don't double count springs and gravity. And then calculate the work. Add them all together. Total is, total. If some of those are zero, write zero. Yeah. Say that again. Is the elevator touching the spring in the part that we're talking about? No. Can springs exert a force at a distance? Then there is no spring force acting on the object at that time. We'll consider the force the spring exerts in the second phase of the class when we're talking about the elevator is. But if he no touchy, he no forcey. Only gravity acts at a distance this semester. Yeah.
What would it mean if it asks what is there work internal?
Is there what?
Work.
Internal work, I call internal energies. We will never deal with those. Work done by internal forces, no, never. Please.
We, study, like in this class specifically, do we study the rate of change of energy?
I have cut that out. That's called power, and work per time is power. It's a thing, but I'm cutting it out for the sake of focusing, getting a couple things right instead of doing everything and being confused. Okay, let's dive in. Let's analyze this. Let's do the problem. The big way we do every single energy problem is change in total energy equals the external total work done. Bam. So let's apply this formula. Change in energy equals Wext. To find the change in energy, what do we need? What does change always mean? Final minus initial. So I'm going to talk about what is my initial, talk about what is my final, calculate these, calculate the external works. And we have identified the forms of these. We have talked about there's a kinetic. There's a kinetic, I should maybe say initial and final. And there's a gravitational potential. There is a gravitational potential. We've identified the force that does this work. It is the work done by tension. Please. UGS, not UGI, UGI. And certainly not UGO. Am I even pronouncing? It's Yu-Gi-Oh, isn't it? Okay. Anyway. Tell how much I know about anime. Okay, so did you guys write the numbers down in the first part? No? Okay, I'll put them as reminders up here quickly. M is 2,000 kilograms. What else did I say? Velocity, the steady velocity is 1.5 meters per second. And acceleration is 0 meters per second squared. Okay, apply what you know. Nah, one more. How far did we go up? From 4 to where? What are we describing? From here to there. Or rather, at the time we're passing the second floor and at the time we're passing the fourth floor. How far up is the fourth floor, by the way? What is Y final? 12 meters. Each floor is 4 meters. I go up. That's 3 fours. Yeah, you see where I get Y final equals 12 meters from? So I should add that to the list. Y initial is 4 meters. Y final equals 12 meters. Ready, set, go. Apply the formulas that hopefully you have memorized. If not, you can look them up, but also take a stern wag of the finger. They're only a few. Okay. I'm going to give you what, 3 minutes? 3 minutes? Talk to your neighbor, check each other. Should I put this in the Google form? Yeah. No. No, it doesn't need to be in the Google form. Oh, what the heck? This will let me see when you're done. Also, Cerny is nodding. Yeah? Yeah? D, E, F. These are numbers, by the way. Still going to walk around and help them. Question? Yeah? Yeah? Gravitational potential energy is mgy. Weight times height. And what's I mean? Always, yeah, in my class, always. Okay, raise I go.
Just say,
No, that's gonna take long. Is velocity initial the same as velocity final? Is mass initial the same as mass final? I mean, did we change mass? Did we change velocity? Then half mv squared can't be different.
Because I'm trying to figure out.
Memorize the house. It's only a couple. Half mv squared, half kx squared.
Do that one. I'm just trying to figure out the equation for UG as well.
Oh, mgh, mgy.
I've given the acceleration to be zero at all the time, right?
For this part, saying we're talking about it as it's rising, as the cable's pulling it upward steadily.
There won't be any.
Yes, there will. There will absolutely be work. Is there a force? Is there a displacement?
Oh, so
Now,
zero
what is the
power.
total work considering gravity external? Zero. If we consider gravity as an external force, but we're practicing applying gravity as a potential energy, just like gravity as a potential energy, then we stop considering it as a work also. So I'm going to talk about there being total work done as well. Yes, Lip. Ah, thank you. Mhm.
So, force is M times A.
Net force is MA. Not every force is MA.
Oh, um,
You can calculate the work done by total force, and then it is absolutely MA displacement,
okay.
cosine theta.
So if it was, MA, we had A 0, so would it be 0?
Total work is zero.
Or would it be-
Total work is zero, but I don't talk about total work here. I'm talking about the work done by tension. Though talking about work done by each force individually, tension work, weight work. Weight work we've boiled into this, encapsulated, solidified into this single idea of potential energy.
Okay. So what equation would I use if I want to find the work of tension, which is what you're asking?
This equation.
This equation?
Yeah.
Okay, so if
What is the force of tension?
the force of tension,
Find the force of tension, multiply it by,
the multiple
Displacement and then
displacement
goes
equals
by-
one.
yeah.
Yeah, displacement's A, because it's initial to the, yeah. Different for held tension is.
What's that angle mean? How do I define that theta?
Tension is just M times.
In this case, it is. What? What's the net force on the object? Net force is zero. How do you know?
Because
A is 0, right? I said A is 0. Two forces acting on it that add to 0. Weight and tension must be equal.
One of those.
So weight is mg. Tension is weight is mg. That's not always true. That's not always true, but in this case, I said A is 0. There are only two forces on it. That's how you get tension.
Yes,
Really?
yes. Yeah.
Yeah.
But if you,
When I write the letters and box them. What? No, you have to ask Mama to. You have to wait till, yeah, well, you have to wait till we're done with this.
Is,
Sure.
so. I assume that there's gonna be. It's the change, so it's final minus initial, so KF minus that, so I assume. Gravity final would be stuck at the 4, so it'd be 12.
Mm-hmm.
And then our initial would be our 4.
Mm-hmm. Yeah, that's
And
right.
then when it
Well,
comes
hold on.
to-
Gravity is not the same thing as height. What's the gravitational potential energy equation? What is U? U is not X.
Very similar to like the change in
That's a true thing, but that's not what UG, I mean, yeah, that's how you can find the gravitational potential energy, but you don't need to think about that. You don't need to calculate the work done by weight anymore. MGY, bam, that's it. Gravitational potential energy is MGY. Memorize that, memorize that. There are only a few formulas in this whole chapter.
I'm planning on memorizing more physics since now that I'm done with them.
Good,
But
just like,
when it comes to the kinetic force,
not a horse, energy,
I mean energy. Doing half mv
squared.
squared. Wouldn't we still need to find the kinetic final to do
You tell me, how fast is it moving at the end?
find velocity?
I gave you velocity,
Gives initial.
and I gave you that it's not accelerating. What is the final velocity? If you have no acceleration, how much velocity changes? What does acceleration tell you? And if velocity has no slope, what is the value? How does the value change if the slope is 0?
So
If you're driving in your car and you don't accelerate, what is 0? Plug in what for 0?
this portion,
But what does that portion mean?
that two,
Squared is how we pronounce that. V is 1.5. V later is 1.5. Later still, V would still be 1.5. Plug in 1.5 to that formula, and that'll give you the kinetic energy.
sorry.
No, you don't need, sorry.
Ask you like if this is like close to correct. I'm not very sure. We're like,
Yeah.
F. Okay.
Good.
Okay.
30 seconds.
There's no such thing as a negative total.
There can absolutely be a negative total energy.
They're not, you can press a spring or you start a spring, both ways you're gonna get
Correct.
going into a system.
Elastic potential energy, kinetic energy can't be negative.
Elastic potential energy and kinetic energy both can't be, because the one variable is gonna be squared.
Okay, time's up. Let's talk about these. What's the formula for K? 1/2 mv squared, plugga, inna. What do you get? Okay, plug in. Thou shalt use a calculator if thou needest. I got 2250, I think. In it? 1/2 mv is 1000 times 1.5 squared. You're right. No, I'm right. 2250. Let's. Okay. Kinetic energy. 1/2 times mass times square of speed. Yeah? Okay, so let's plug in numbers. What's 1/2 times 1,000 times the square of 1.5? Ha ha ha. Sorry, I was already doing the half. Okay, so let's multiply this out. Okay, so let's evaluate this. What's 1/2 times 2,000? I think that is also goes by the name 1,000. What's 1.5 squared? 2.25. How I do this internally is instead of 1.5, I call it 15. 15 squared, 225. Then take care of the point. So I think my kinetic energy starts at 2250 units. Energies are always in joules. Energies and works are joules. Okay, initial kinetic energy, just the kinetic energy, 2250. What about the final kinetic energy? Stays the same. How do you know it stays the same? No change in the velocity. I told you acceleration is zero. If acceleration is zero, velocity cannot change. If velocity does not change and the passenger isn't throwing things out the hatch, or I don't know, if the mass is not changing in some way, has to be the same. Okay, what's the gravitational potential energy equation? UGH. What? MGH. Or as I'm talking about Y initial and Y final, I mean, what is H? The height relative to reference. I talked about this as Y, so I'm going to plug in Y. Y is height just as much as H is. It's just a different letter for the same thing. So what's M? 2,000 times G is, oh my God, let's say 10 times Y. Well, I start out initially at 4, and I end up finally at 12 meters. What does that turn into? 2,000 times 4 is 8,000. Times 10 is 80,000. Units? Always joules for energies. What's 12 times 2? That's 24,000 times 10, 240. Okay, and if you plugged in 9.8, do I care? No, doesn't matter. I'll let you do that. On an exam, I would never include 2 questions, 2 answers that are just different by that and expect you to guess which one I used. Okay, questions about how I got either of these quantities, any of these 3 quantities. Any questions on gravitational potential or kinetic? Please, squeak now. No, I don't think there are no questions. Google Form G, ask me a question, or if you don't have a question, tell me what your classmate is confused about this part, okay? Rat them out, yeah. Oh, we got a verbal one. Okay, shh. Before you do that, let's listen. Yeah, but first we got to solve for the individual parts. And if people are having trouble with what is kinetic energy, I wanted to do those separately. Yeah, so G is ask me a question. Tell me where you're confused about this part, about just evaluating kinetic and potentials. Yeah. Okay. 10 seconds to finish up. I'm going to answer a couple of these. Okay, question uno. Why do you add potential energy to kinetic energy when moving up, would you do the same thing when moving down? You always add together all the forms of energy that apply when you want to find the total. That's what total means. What's my total bank account? What's my total net worth? Well, I would add together the worth of everything that I own, of all my bank accounts, and subtract whatever debts I've got. Is there a way to sanity check our answer? No, not yet. How to know when an energy is negative? The only way I could think of for an energy to be negative is if you're below y equals 0, then there would be a negative gravitational potential. Kinetic and elastic potentials can't be negative. Why do I add gravitational to kinetic energy? Because I want to find the total in a second. Total is all the forms added together. When do I include negative in the kinetic equation? Never. Why don't we count work in the change of energy? Because I haven't done that yet. First, I'm helping people understand the individual equations, then we'll get there. Is there a way to know what equations to use? Yes. Is it moving? Use kinetic. Is the height changing? Consider gravitation. Is a spring compressing or extending? Use elastic. Is another force acting that is external to the system? Calculate its works. That's it. That's the 4-step process that we did before. So the total energy, if it changes, that's equal to the total external work. Find the initial energy, find the final energy, subtract them, set it equal to work. That's all that you could possibly do with energy land. Exactly. You apply every form of energy that is involved. Just like with forces, when do you know whether to include a friction force? When it makes sense to. There is no, the checklist is think about that, visualize the problem. It's not when you see letter X, answer is 3. I can't condense it down to something that doesn't involve think about the scenario that's going on. Okay, so let's plug these in. Further questions, good, great. I can't hit every single one. Please ask me after class. There were some other good ones. I'm just not able to hit every single one. For time reasons, 80,000, 240,000. I can write 4s. Okay, so let's find that initial and final energy. Total energy. I can add 2 to 80, 82 to 50 joules, 242 to 50 joules. And then the external work, I didn't do that before. I wanted to focus on the individual pieces one at a time. What does the work again? The only force that is acting on it, that is not already accounted for in gravitational form, gravitational potential energy, tension. Now here's a question. What is the tension formula? Trick question. There is no tension formula. You always have to deduce tension and normal force from the external, and for that matter, static friction, from the externals of the problem. Now, what does it make sense for tension to be here? And how do you know? Come on, please. What's tension force? How do we find it in this problem? What is the mass times acceleration? That's not correct. Normal force is not equal to ma. All the forces. And what's the value of that in this problem? The summation of all the forces is equal to what is F equals m times A tell you? Equals all the forces equal, Gene? A is 0. So I'd say F equals ma means F is 0. What's F? Total force. So F equals ma tells us total force is 0. So if total force is 0, is tension 0? Is there more forces than tension? What is mg? Be precise. Yeah, but what is that equal to? Is that always tension? No. In the back, you're on track, but I want to get lots of people. Yes. Weight force, go on. Exactly. So to summarize, because I'm saying lots of things out loud, here is the logic of how to find tension. This goes back to what we did back in the last, in module 2 dynamics. Don't forget this stuff. Tension has no single equation, but I do know a very important equation. I told you the value of acceleration is 0. So F is 0. That means total force is 0. Not just any force is 0, total force is 0. In this case, tension minus weight is total force. Okay, so what could I conclude? Which is bigger, T or W? Google form! Google form H, which is bigger, tension or W? I have deduced total force equals tension minus W equals 0. Which force is bigger? That is Google form H. Is the magnitude of tension bigger or is the magnitude of weight bigger? Which is stronger? If tension minus weight equals 0, which one is bigger? Yes. Okay, you know what I'm asking? Okay, let us apply the dread methods of algebra to this equation. I add W to both sides, and I deduce that tension equals weight. They're the same magnitude. Although opposite direction, yeah. Okay, so what can I plug in for the weight formula? Is tension always mg? No, but in this particular case, I can absolutely plug in mg. M2000, thank you, G. Am I done? I'm done with finding tension. What was I trying to do anyway? W. Now W equals mg, right? That's what I just said, right? Am I done? Does W equal mg? Context. Context. I'm talking about not weight here, but work. Energy, 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 right? If I want to find work, work and weight both start with the same letter. We both talk about them as W, but context here, if I want to find the work done by tension, work isn't force. I would use the force times displacement equation. Okay, what is the force? What is the displacement? Eight times 80,000. Right? Isn't that what I just calculated 2 seconds ago? 20. I can remember things for 2 seconds. In my dreams. Okay. Question.
We went to the fourth floor. So shouldn't it
Passing. You tell me what delta means. What is delta? Final minus initial. I start at 4, I end at 12. Or I'm passing through 4, passing through 12. Question in the back. I applied the principle of PHMA. And I deduced that if there's no acceleration, tension and weight had better darn well balance. I don't have an equation for tension, but I do have an equation for weight. Bam, done. You don't like that. Talk to me. You still don't like that. Your eyebrows don't like that. No, she's asking about how we found tension. I want to. Yeah, happy with that? Okay. Don't forget your force methods just because we're on a different chapter. Final includes everything. Okay, so what? 20,000 times 8 goes by the short name 160,000. Now let's compare these values. I start with 80. I end with 240. Is that change in fact equal to 260,000? You betcha. Don't you know? Wait, hold on. There's a thing that I didn't double check. I already told you the punchline is this is correct. Work is not just force times distance. What else is missing there? Plus or minus or zero, the cosine of the angle. When is force positive? When is work positive? When they are pushing in the direction of motion. When is force negative? Always. When is work negative? When the force is pushing against the displacement. When the force is helping motion positive. When the force is hindering motion negative. What about when the force is at right angles to the motion? Zero. How much work does an inward force of gravity do on the moon? Is the moon speeding up? Gravity is pointing, well, this way. The moon is going this way. No work because the force is at right angles to the direction of motion. Radial and tangential are perpendicular. So this is positive or negative? Positive. Are you sure? I'm positive. Okay. So, and you can check, 240 minus 80 is in fact 160. Right? Right? Yeah. And the 2250 and the 2250 die. Question me. Tension is up and the displacement is up. You betcha. What if I had a friction force? Which direction would the friction force be? Which direction would the displacement be here? Which way is it going? Is it? If I add in a friction is preventing what? If friction is down, then that must mean the elevator is going up. Friction opposes the relative motion. You would have an up friction if you were dragging something down. Friction and displacement are nearly always going to be in opposite directions. Friction is always sucking energy out. Other questions? We have time, a smidgen of time. We don't have time for you all to do all the parts of this. I would like you to start, identify what kind of energy we have Our initial is going to be where we ended with here. Remember at the beginning of the lecture, I said we're going to start as we pass the 4th floor. My mischievous little mischief maker is going to snip the cable. Yeah? Okay, so we're going to start at the instant he snips the cable. We are so many meters up, 12 meters up. We are moving at 1.25 meters per second. So this is our initial energy. What form or forms of energy do we end with? Put that in Google form, I. What form or forms of energy do we end with? After he snips it and it falls and we're compressing the spring. Ultimately, I want you to find how far does the spring compress? So at the instant of the spring's maximum compression, yeah. I just want you to identify what kind or kinds of energy we have when the elevator is brought to rest by the spring. And I will write that down. Thank you. When the spring has brought it to rest.
So I'm gonna figure out. What?
Not elephant. Elevator. Let me also put J. Are there any other forces that act during this boing motion? Are there any other forces that we need to calculate work of? That's question J. Chop chop. Okay, the correct answer for I is when we have reached maximum compression, the elevator is not moving. There's no more kinetic energy. We are as close to the ground as we're gonna come. We're on the 1st floor. Yeah, you might not be exactly at y equals 0, but I'm gonna hand wave away. The remaining gravitational potential energy is small compared to our initial. We're going from 24 meters down to really close to 0 meters. So I'm going to ignore any gravitational potential energy. Is there any spring elastic potential energy? You betcha! We got a spring compress. So the correct answer, what I would say, is only UE, elastic potential energy. Are there any works during this phase we should consider? Is there tension force? No, the string is cut. Is there friction force? No. Is there normal force? Is there spring force? But we accounted for spring. That's the spring potential energy. Is there weight force? Yes, but we accounted for it. There are no other forces to account for. So the correct answers that I'm looking for are UE and no. Okay, 2 more seconds, 2 more seconds. We are accounting for the weight force whenever we use gravitational potential energy. We don't need to talk about the work done by weight and the energy stored by weight. Yes, we did. Yes, we did. That's where the 160,000, I'm sorry, the 240,000 and 80,000 came from. When I wrote down total energy, that's the majority of the energy. No. Okay, so we started with 242,250 joules of energy. This is now our initial energy. 240, what? 242, 250? E final has only one form. And what's K? I gave you 500,000. What can you conclude? Question K is find final compression. Ready, steady, go. Please tell me. Good. Any questions?
Isn't it the X part of it, like the difference in meters, or are we just accounting for all?
Distance in meters when? Distance in meters of what? Half kx squared is talking about what object? What are we talking about? This is the what potential energy?
Oh,
Yeah, so we're talking about the spring's change in length, not the elevator shaft. That's the question.
like, oh.
That's what I want you to find. I mean, at the end, always go back and reread the question. Yeah.
That's the same thing as before, is it? Right?
Yep.
Okay.
Good. Okay, in the last 2 minutes of class remaining, what's X mean in this equation? The spring compression. How compressed the spring gets. In other words, what the professor asked for. I solve for this equation. And it's roughly 98 centimeters, 0.98 meters. Okay, I will stick around at the front to answer further questions. I love each and every one of you. You are all awesome people. I will see you on Monday. And if you